us look at chapter 8, section 2, different sequences and Stirling numbers, 8.2. Different sequences and Stirling numbers. This is the last section on the exam. Okay, so given a sequence hn, n is equal to 0 to infinity, define a new sequence delta hn from n is equal to 0 to infinity, where delta hn is equal to the difference between hn plus 1 and hn. So it's the difference between the next term and the current term, right? So we can look at delta as an operator, view delta as an operator that acts on any sequence, hn. N is equal to 0 to infinity. Okay, for example, if you take hn is equal to n squared, then my original sequence n squared, n is equal to 0 to infinity, gets sent under delta to n plus 1, right? N is equal to 0 to infinity, because hn plus 1 minus hn is equal to n plus 1 squared minus n squared is equal to n squared plus 2n minus 1, plus 1 minus n squared, which is 2n plus 1, right? Well, but I can do delta to this again, right? If I do delta to this again, I get some sequence. Let us see what is the sequence I get. Well, in this case, hn plus 1 minus hn is going to be 2 times n plus 1 minus 2n, which is 2n plus 3 minus 2n, plus 1 minus 1, which is exactly equal to 2. Therefore, I get the sequence which is just 2 every single time. And if I do a final delta to this, well, every single term is 2, so my final sequence is going to be 0. And I'm calling this the final sequence because how many ever more delta I hit it with, 0 minus 0 is always going to be 0, and it's going to be continuously this exact sequence, right? So let theta be the sequence. Theta is equal to the sequence 0, and is equal to 0 to infinity, which is just equal to 0, 0, 0, dot, 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 right? So for any r greater than 0, for any r greater than or equal to 0, we define delta to the r as just applying delta r times, okay, with delta to the 0 means do nothing, is equal to do nothing. So the same way as you take derivatives, first derivative, second derivative, third derivative, we are taking the difference operator delta, and it's doing first delta, second delta, so on. So I have delta 0 of hn is equal to hn, delta 1 of hn is equal to just delta hn, delta 2 of hn is equal to delta of delta hn, and so on, right? Then we saw that then delta cube of hn sent, well, maybe I shouldn't use theta, maybe I should use I should just call it 0, big 0, okay, 0 with maybe a special symbol. Okay, this is my 0. Send my sequence n squared, n is equal to 0 to infinity, to my sequence 0, right? Because applying delta 3 times sent it to 0. What if I looked at delta to the r hn? Well, I don't need hn here, actually. What if I applied delta to the r, where r is greater than or equal to 0? Then again, this also sends n squared to 0 for every r greater than or equal to 0, greater than or equal to 3. Right? Because after 3, you're hitting 0. After that, you'll continuously keep hitting 0, right? So if we want to do it more explicitly, we can write this down as 0, 1, 4, 9, 16, 25, 36, 49, dot, dot, dot. Let us look at their differences. 1, 3, 5, 7, 9, 11, 13, dot, dot, dot. So this is my delta 0. I have now applied a delta 1. Now I'm going to apply delta twice, which would give me 2, 2, 2, 2, 2, 2, dot, dot, dot. Delta 3, 0, 0, 0, 0, 0, dot, dot, dot. Delta 4, 0, 0, 0, 0, dot, dot, dot. And as I go on, this is all going to be 0 all the way. Right? This is called the difference table. Difference table. Okay. Oops, let me stop this video here.